Is that good? Okay, fine. Thank you. Right, I would like to begin by thanking all the organizers, especially Giorgio, who invited me here to share some of our work with you. I will be talking about particles and fields in superfluid turbulence. I had thought I would concentrate only on particles, but after some of the questions that came up during the discussion session, I will also tell you a little bit about the statistical properties of the fields as we go along. This work has been done with my current graduate student, Akhilesh, who has benefited greatly from interactions with Mark, who's right here. He's been helping us a lot over the years. And Vishwanath Shukla, some of you know him. He is now at the Institute of Technology in Kharagpur. Actually, there should be another person up here. That's because I introduced more of the fields thing, and that's Obhik Basu, who is at the Shah Institute of Nuclear Physics in Kolkata in India. And I would like to acknowledge support from all the funding agencies, in particular the Indo-French Center for Applied Mathematics, which has helped our group to collaborate a lot with our colleagues in France. Okay, so here's an outline for this talk. An introduction on superfluid turbulence, which is more or less redundant for this audience, but I will go through it just to establish notations. Then I will define the models that have actually already been defined by several other speakers before me, but just for the sake of completeness, I will do so also so that you know what notations I am using. I will then tell you about the direct numerical simulations that we have carried out to study a wide variety of properties of superfluid turbulence by using these two models, some results and some conclusions, right? Please feel free to interrupt and stop me with questions, etc. during the talk. Now some prehistory. This is to set the stage for what we know in fluid turbulence, and there is no way I'll cover all of fluid turbulence in a few minutes, but let me highlight a few things. It's a very beautiful work, probably the only experimental paper that Mark wrote. Is that correct? Of visualizing, regions of high concentrations of vorticity in a conventional classical fluid that is turbulent. And then there are these iconic pictures from the group of Yukio Kaneda in Nagoya. This was when the Earth simulator was still the world's fastest machine, and what you see is this green forest, but if you zoom in and zoom in and zoom in, you will see that these greens are actually, vorticity tubes. This is in an isovorticity plot. So these things exist in fluid turbulence. And we can study the statistical properties in many, many ways, some of which I will recapitulate when I start discussing the statistical properties of superfluid turbulence. Then, of course, there are particles in turbulence. For conventional classical fluids, this is a huge, huge field, which was always known to the engineers. For example, there's smoke coming out of chimneys. There are pyroclastic flows that occur when a volcano goes off, industrial flows and clouds, all of which are very important. And there's a long history of studying these problems, also from a more fundamental physics point of view, in the turbulence literature. And as we go along, I will see what we can learn from what is known from the classical fluid turbulence literature by applying it to the superfluid turbulence literature, where, as you know from the earlier talks in this meeting, there is a lot of reason to study particles and superfluid turbulence also. But if I might say so, these studies are in their infancy compared to what is known for classical fluid turbulence. Now, suppose we know how to do classical fluid turbulence, by which I mean that we know the Eulerian velocity u of the fluid. Okay. at the point x and t, then how do we study the motion of a so-called heavy inertial particle in the flow? And the v is the velocity of the particle, and this is how the particle position evolves, okay? And if you have Lagrangian traces, then v is just equal to u. And now a new parameter has crept into the problem, which is tau sub s, or the Stokes or response time of the particle, okay? With the particle has diameter a, I'm sorry, the symbols are not the same. Nu is the kinematic viscosity, and rho sub f is the particle radius and density, respectively r, and there should be some, a is the particle radius, all right? So this goes back to the work of Maxey, Riley, and Gatignol, and this is true for heavy inertial particles. If the particles are light, you have to add more terms, and there's a huge history of work there, but I will not go into all that at the moment. I will just confine myself to such heavy inertial particles. I should also point out that these particles are passive insofar as they do not affect the flow, but they are advected by the flow according to these equations. Now, when is such an approximation justified? It is justified when the particle radius is much less than the Kolmogorov dissipation scale eta, below which viscous losses become significant. The particle interactions are negligible. The particle density is much greater than the fluid density. Typical particle accelerations exceed considerably the acceleration because of gravity, and the particles do not affect the fluid velocity, which I have said already. Now let's go to the subject of this talk, which is particles in superfluid turbulence. So again, the standard slides, which remind you about what is superfluid turbulence. There's this often quoted statement by Feynman that it is a tangle of these vortices, and here is a simulation. I'm sure it must be from the Newcastle group, and here is a cartoon of something being spun around and generating these quantum vortices. And experimental systems keep on increasing with time. There's, of course, good old helium-4, then there's helium-3, and Bose-Einstein condensates, and so on. But I think most of the experiments which have been done with helium-4, if I'm not mistaken. All right. Then there are levels of description. I mean, this was said much more colorfully by speakers before me, but I will say it in a sort of just straightforward way, which is the Gross-Pireevsky equation, which is good at low temperatures. Okay, we can go to finite temperatures, but we'll get to that later, probably in some other part of the talk. Low temperature, weakly interacting Bose gas, unless you start fiddling with the potentials. And then this accounts for phenomena at the length scale of the superfluid vortex core, which has a healing length psi. Then there is the vortex filament model. You have heard many talks about that. It distinguishes between individual quantum vortices, ignores the nature of the core, and is valid at length scales greater than psi, and it's in the incompressible limit. There is this two-fluid model associated with the names of Hall, Vinen, Bekharevich, Khalatnikov. It does not resolve individual quantum vortices. So they've got a macroscopic classical vorticity field, so strictly speaking, it requires some polarization of quantum vortex lines in some region so that you can get an effective classical vorticity out of it. And then there is this a kinetic theory model and wave turbulence, all of which you have heard about in this meeting, though not too much about this. And the color code here is the blue I will not talk about. The red is what I will talk about. All right, and this picture, which is sort of semi-iconic by now, the experiments done at Maryland when Greg Bewley was a PhD student, and he was using hydrogen snow, or just frozen pieces of hydrogen, or even later deuterium, and they seem to go and sit on these vortex lines, and it became a nice way of visualizing these vortex lines. And as Giorgio pointed out in his talk yesterday, these particles are much bigger than the vortex core size, so eventually you have to understand how all this happens and what tracking. And I think this field is ripe for theoretical investigations now, because there are lots of questions, both fundamental and applied. So again, what are the levels of description? So first, let us proceed the way I had written it down. At the most coarse-grained level, that is the HVA model. This is the coarse-grained model, valid on scales of many intervortex spacings. All the numbers have been given to you by my colleagues earlier in their talks. This is an extension of the two-fluid model of Landau and Tisa, but it is much more. And what is much more is given in these equations here. You have seen them already, I think, in the talk of Dr. Komenko. Right? I think he also studied that. In fact, I will also give you some complementary data. So it's basically Navier-Stokes for the normal fluid, which is indicated by the subscript n. And this, if you like, is the forcing term for the normal fluid. Ignore this term for the moment. And then there is, strictly speaking, should be Euler for the superfluid. And these are sort of interpenetrating fluids, which is a sort of way of thinking about it. But I have added over here a viscosity, even though it's a superfluid. I'll give the justification was already given in the previous talk by Dr. Komenko, but I'll get there again. And both fluids are incompressible. And then they are coupled by these two terms, which are the so-called mutual friction terms. I have written them down here for the sake of completeness. If you're not an expert, please don't look at all the details. Omega sub s is superfluid vorticity and so on. I want you to note that it depends on the fraction of the superfluid, rho s over rho, and the fraction of the normal fluid, rho s over rho. I think I got all my signs right, but please forgive me. Then there are these coefficients, b and b prime. They are the so-called coefficients of mutual friction. And thanks to Professor Barengi, I think we have them as a function of temperature, measured in helium. Is that correct? Yes. It's on your, exactly. So anybody who works on this field, if you want to do it seriously, please go to the website. And there you will find the temperature dependence of B and B prime, and also the temperature dependence of rho s over rho and rho n over rho. So even though it's not a microscopic description in the terms of wave functions, it's a handy description, and if you want to model helium-4 in 3 dimensions, it's a good starting point, and you can actually plot then, because of these measurements, all quantities as functions of temperature. I said in addition to the kinematic viscosity, the normal fluid, we've included an effective viscosity, perhaps first included by Wienen in the superfluid component to mimic this dissipation because of vortex reconnections and interactions between superfluid vortices and normal fluids. These are the standard words that you find in the texts. And at a practical level, you really need that nu sub s, because if you run your code without nu sub s, it blows up pretty rapidly. Okay, but in any case, nu sub s is much less than nu sub n, and those of you who have done such simulations will know that that will be challenging immediately. If anybody has done MHD away from magnetic Prandtl number 1, you will understand what I mean. Okay, many references, I can give you those as we go along. So that's for the field. Those are the two fields. We have a normal fluid and we have a superfluid. Now we want to put in particles at the same level at which we put them into classical fluids, a la Maxi, Riley, Tignol. And so there we go. That's the change in the position. That's the particle velocity. But now we have two such terms. That's the most natural generalization. Recall that we had U minus V, so now we have UN minus V with a 1 Stokes time, another US minus V with another Stokes time, and so you have yet another control parameter, which is the ratio of these times, which is also equal to the ratio of the two viscosities. Okay? All right? So that's what you have to do. If you have these equations and you're accustomed to such things, you can do this by using a pseudospectral method to simulate these HVBK equations. Then you use the Eulerian velocity fields for the normal fluid and the superfluid, which come out of your pseudospectral simulation. Put them into the equations for the particles. And there, okay, you whatever your favorite scheme is, this one works pretty well, just a forward Euler scheme. And then the particles will go off your Eulerian grid. So you will have to do some interpolation to get the the Eulerian fields on those points, and you can use works reasonably well, and so on. So I don't want to hide anything, but I don't want to bore you with details either. So we've done many, 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 many runs. Okay, I'm just giving you some illustrative ones with some illustrative parameters. But if you want the details, you have this paper on the archive, and you can look at this for the fields part of it. The particle part of it, you will see, I hope, no later than next week on the archive. So some people had asked about spectra. What do we know about spectra? So if we live at the level of these HVBK equations, these are the spectra we get. So this is the energy spectrum for the normal fluid versus K log plot. That black line is the K to the minus 5/3 Kolmogorov, and this is the analog for the superfluid. If you look, the tail of the superfluid is a bit further up, and that's because the viscosity for the superfluid is much lower than that of the normal fluid. And again, if you want to be careful, you want to resolve these tails well. For the experts, K max eta must be not terribly different from, bigger than 1. It becomes difficult as you keep on doing it. I should also point out that these have been done by their group also. And yes, yes. I'm sorry? This coflow, this is not counterflow. And we had forcing terms in both equations. We find it useful to force the one which is dominant. So if you have more superfluid, we force the superfluid equation. If we have more normal fluid, we force the normal fluid equations. The different colors are different temperatures, which you probably cannot see from there. But this is 1.3, this is 1.8, and this is 2.17. And when I make these plots of temperature, that's all with these B prime, rho n over rho, which we find on Professor Barengi's website. Okay? Yes? I mean, I just said it. I mean, it's conventional in the literature because it's supposed to model reconnections and so on. It's completely phenomenological, and it's also a practical necessity because otherwise the codes tend to blow up. But it is much, much less than that. Here it is factor of 10, if I've got the numbers right, but they're all in that paper. Yeah, I understand. Look, I completely understand. I'm just telling you what is the best we can do and the general words that go with it. I cannot start with Gross-Pitevsky and derive the HVBK models, and nor can anyone else. Okay? So it's just a different scale, and we think this is the best we can do at this scale. Yes? Yeah, so it's very close. So it's okay. It's just epsilon below. Okay? Yeah. Right? Which, sorry. No, I understand. Yeah, probably. Okay. It's there. There is a little tiny bit of superfluid. Yeah. Right. Yeah. It's just mod USK squared. That's Now you can ask about fluxes. So all the fluid turbulence experts, I don't need to explain, this is the energy flux from K to K plus dk. If there is actually an inertial range, this should be flat. Okay, in the inertial range, well, this is the best we can do. Probably your group has a slightly bigger resolution, I don't know. Yeah, but it's not possible to do very much better than this. Again, these are the three temperatures that I talked about. And again, you can see the differences in viscosity lead to differences here. So far it is looking more or less like dandied up classical fluid turbulence. You can also worry a little bit about what's called mutual friction transfer. I won't bother you with details, but there is significant transfer between the two fluids in the range of scales that we are calling the inertial range. Now, if you go back and look at the HVBK equations, there is a term in each one there, UN minus US. So if it so happens that UN and US are completely the same, then that term disappears. Okay? So you can ask, can I quantify how much they're aligned? And we have done this. We did this first in 2D. That was with Vishwanath. Now we've done it in 3D also. You can look at the ratio of the magnitudes of this, and they have power law tails both at small gamma and large gamma, which we can understand qualitatively, well, actually semi-analytically, but I won't get into those details here. And you get nice power laws. These are cumulative PDFs. You can also look at the angle between UN and US, they're vectors, okay? And you can plot a PDF. I'm sorry if you can't see this very well. So this is P of theta, that angle, and theta over pi on log-log scales. At low theta, there is a slope of 1. At large theta, there's a slope of 4, the right sign. And again, by making suitable, simple Lanzetze, we can actually get this, though I'm not showing it here. I will show you the standard way of doing it for another such PDF in a minute. So we can quantify the alignment of these. Of course, I don't know how an experimentalist would measure such things. That'd be a considerable challenge. But it's there. At least in the numerics, we can measure some things quite easily, which would be difficult in experiments. Now, structure functions, Laurent defined them the other day, so I have defined them here too. This is, again, a standard method of analysis in classical fluid turbulence. So you take the velocity difference, same time, for the moment anyway, at 2 different points. That's called a velocity increment. Let's take the longitudinal increment, and then you take this longitudinal increment, raise it to the power p, and take its value over the non-equilibrium statistically steady state of turbulence. And then you find that if this R lies in the inertial range of scales, that it is smaller than the energy injection scale and much larger than the scale at which you have significant dissipation, then you should find the power law here. And we will talk about the power law in a minute. But I should point out that there's this celebrated result, which Laurent also mentioned the other day, called the von Karman Howarth relation, which is exact, which doesn't depend on any sort of measurement, etc. Start with Navier-Stokes, assume that there is a statistically steady state, and you get minus 4/5 epsilon r for the third order structure function, where epsilon is the energy dissipation rate. This is one of the few exact statements in classical fluid turbulence. Okay, starting from Navier-Stokes. Now, what do we know? If we follow the old Kolmogorov 1941 theory, then this exponent zeta should be a simple function of p, linear, p divided by 3, which is shown by this black line on this plot. But experiments favor so-called multiscaling. Zeta p is a nonlinear, convex, monotone, increasing function of p, which is shown by the red plot here from some shell model. Doesn't matter, but this is just to illustrate what I will mean by multiscaling in this talk. Okay? So, at the HVBK level, do we have multiscaling or do we not have multiscaling? Okay? We do, but let me just, since I put von Karman Howarth here, if you do the details, and I'm telling you that they are quite messy, so I won't give you the details. The analog of the von Karman Howarth equation is 4 different equations, and there are so many symbols I won't even try to explain them to you. But there are different velocity increments. The normal and the superfluid get scrambled up. There are longitudinal and transverse, and they're all given in this paper which I referred to earlier. And I also want to point out that you have to include the contributions from the mutual friction part. And at the end of the day, you really have 4 equations. Okay? This is the most complete but simplest analog of von Karman Howarth. Nothing simpler. Okay? Sad but true. Okay? So if you want that, that's what it is. Now, get back to numerics. Can I measure these multiscaling exponents for structure functions? How am I doing for time? Terribly? Okay, good. That's fine. All right. So you can measure this from the HVBK simulation. We can measure these structure functions both for the normal fluid and the superfluid. Over here, I plot the exponent that we fish out versus P. And those of you who can still see what's on my axis, this is the ratio zeta Pn over zeta P3, which is a way of extending the range. Those of you who are experts already know it. Those of you who are not can ask me during the coffee break. Okay? And then we get such plots, ditto for the superfluid component. And then since we have everything as a function of temperature, we can ask, what does this ratio do as a function of temperature, which we have thanks to the measurements of B and B prime, rho n, etc. That's what it does. By definition, the third order is flat. And then this is, these are real error bars, not just, this is with fitting, local slopes, and all that. It is advantageous to plot it as a difference from the Kolmogorov value for the temperature. And these are the error bars. But you can see that there is an enhancement in the region around 1.8. And these data are completely consistent with those in that paper. Of course, one of the authors is right here. Okay? And this calculation is done completely independently. And this is also consistent with what is seen in the Prague experiments. Correct? Is that fine? But not in some other experiments. So I think we all need to work some more. These error bars are that big. I mean, I'm very conservative when it comes to error bars. But, okay, that's the best we can do at the moment. Well, I mean, of the local slope, the ESS plot, we identify some region, we do a local slope, min and max, yeah, exactly. Very conservative. Okay, it's not what comes out of your MATLAB code. Okay? All right, now get back to particles, okay? I mean, really the talk is about particles. If you look at the literature in classical fluid turbulence on statistical properties of particles, turbulent flows, one of the things that people worry about a lot is that the acceleration, the normal component or the tangential component, all have fat tails. Now, probably you can't see every detail from there, so please don't look at it. Just note that here, too, we have fat tails, and they depend on the Stokes. So here, there's a dependence on the Stokes for the normal fluid, and as you increase the Stokes, this tail comes in. And you can actually do here, which you cannot see very well, a sort of contour plot in the Stokes normal and Stokes superfluid plane, and see how the RMS value of these PDFs change. Similar story for the tangential acceleration of particles, fat tail distribution. So this is what the group of Bodenschatz did several in the early 2000s for classical fluid turbulence, fat tail distributions for accelerations. So, well, we should find them. So if you could put enough particles into your superfluid turbulence flow and don't start looking at microscopic details of vortex core and so on, you have inertial particles which are passive. You should see this. So it's a challenge to our experimental friends. Please do like the classical fluid people do, put in, I don't know how many, Giorgio and people who have lots of computer time, put in 10 million particles, 100 million particles. Okay, and they can probably get better statistics, but this is the thing. Yes? Okay, I should look that up. Thank you for telling me. All right. There are other things that you can do which are more amusing if you have a mathematical bent of mind. Now that you have a trajectory, you can actually do what they teach you in differential geometry. You can keep track of its curvature. You can work out its torsion. These are the equations which have been mentioned in some other talks too. So, and you can express this curvature and the torsion in terms of the velocity of the particle or its normal fluid acceleration and so on. Once you do this, you can find their PDFs. And lo and behold, they are power laws. These are cumulative PDFs. And they have actually nice powers, for example. Okay, can you hear me? Yeah, fine. All right. And we are conservative people, so we put local slopes and so on. Similarly, for the torsion, there's a nice simple power -2. And it's the same reason also. I said that some of these can be obtained analytically, so let me show you illustratively one such calculation. I think it's a battery problem, all right, so if you look at the PDF of the curvature, you can all right, so so let's say that P of A comma V is the joint PDF of the normal acceleration and the velocity, and then you do this and you get that. Similarly for the torsion. Now there is an ansatz that goes in here. A n is a small scale quantity. You can actually get this out from PDFs. E is a large scale quantity. It's sort of like Kolmogorov's clear separation of scales. Therefore, we can replace this PDF, joint PDF, by its product, and then you can note that your data, which is also consistent with classical fluid turbulence data, that these PDFs for the velocity are consistent with the Maxwellian, and that you can fit these ones for the acceleration to that form. You put these in, and you get those power laws. Okay? So there's a semi-analytical way based on some reasonable ansatz, which actually gives you these powers. So when you do these measurements, this is what you should find, even in superfluid turbulence. There's another one for the angle between fluid and particle velocities. I didn't put it up because it is such a heavy figure, it takes forever to load. Here also we can understand the power. There's another thing which I will do very, very fast so that I can also get to the Gross-Piderewski part of my talk, which is, how can you characterize at this level how much time a particle spends in a vortical region? And we did this somewhat recently for classical fluids. The way you do it is by using these objects called Q and R. Q and R are obtained from the velocity derivative matrix. And in the QR plane, you can plot a PDF as a characteristic teardrop shape, which I will not bore you with today. And those who are experts know it anyway. Roughly speaking, in the top half of the QR plane is where you have vortical flows. So you can then condition things on vortical flows. That is, if you are in the QR plane where the particle is already in a vortical region, how long does the particle take to leave that region? This is what in statistical mechanics would be called a persistence time. We introduced this first in the context of 2D turbulence in classical fluids, where it's a power law. So the statistical mechanics people like power laws. But in 3D, because of vortex stretching, it's always an exponential. Exponential means it's a straight line on semi-log plots. From the slope of this straight line, you can extract a time. And that time then gives you the time that the particle spends in the vortical region. So at the HVBK level, we have the same data. We have it for all Stokes, all things I'm not showing you everything. We have it as a function of temperature. So we can actually tell you how long particles will spend in vortical regions in such a model. Okay, then you can go and check in experiments if enough data. Experiments, it's quite challenging to measure velocity derivative matrices because you have to resolve the field, the Eulerian field, at very small scales to get good derivatives. Okay. So let me conclude the HVBK part. I mean, we have shown how to study the statistical properties of such inertial particles in superfluid turbulence. One thing I didn't cover, I mean, people also measure fractal dimensions. That we have not done, but it's straightforward. It will be the same as in classical fluid turbulence because everything else is the same. Then you can look at the acceleration PDFs. They're similar. They depend on Stokes, and they decrease with increasing Stokes. You can get PDFs of the curvature and the torsion. The exponents you can rationalize in the way that I did. And by using persistence time PDFs conditioned on the values of Q and R, which you get in the velocity derivative matrices, you can characterize how long particles stay in vortical regions. All right, back to the experimental picture. But suppose I was not happy with this HVBK description. I really wanted to see what the particles do at the level of the, the quantum of circulation and so on. The long history of earlier studies, of course. This is some calculation that we've been doing with Mark, and in his talk yesterday, Giorgio introduced you to this, but let me do it one more time. So here is the equation we like. This is Gross-Piderewski. There is a symbol here, P sub G. P sub G is something we do in any case in any pseudospectral simulation. It is a Galerkin projector, which in Fourier space says beyond Kmax we set all modes to 0. And I won't get there today, but that also helps us to do finite temperature in some way. That's a chemical potential. And here is a potential for particles. Let us say we allow for n-naught particles with position qi. And in the experiments, as I said, at least the early ones, the particles were quite large compared to the vortex core size. So we can think of a Newtonian description for those particles. So that's good old Newton, all right? There are two forces. One is the external force that we might choose to put on the particles. And then there is the force because of the fluid, which we can actually write down in terms of the size and so on. And if you look at every detail, which was also put up by Giorgio, you can actually compute this object. Once you compute this object, you can find how the particle evolves. Now, I should mention something, which again Giorgio mentioned. These particles are active. Active not in the sense of active matter, but they're active insofar as even as the flow, the superflow affects them, they affect the superflow, right? Which was not the case in the HVBK study that I told you about. All right. Then you can look at various different energy components, the energy in the field, the kinetic energy of the particles, and then we also put in a short-range repulsive energy between particles when we have many particles. I will tell you why we do that in a minute. So this energy in the field is quite obvious. That's the kinetic energy of the particle, quite obvious. And in addition to this, we now put a repulsive interaction which, for no very good reason, I mean, just like Leonard Jones, the 1 over r to the 12, there is no good reason. We just put in something which is sufficiently repulsive at small r. We put it in because you will see there is a superfluid mediated attractive interaction between particles. And if you want to overcome that, you need a repulsion, which will be there in any case. If you shoot two solid particles at each other, they will not overlap. Okay, and if you do things right and you put in your projectors properly, you conserve the total momentum and the number of bosons. How do we parameterize the particles? We parameterize them as Gaussians. So here's the Gaussian, and then dp controls the particle size, and v naught controls the strength of the interaction. And of course, you see the particle displaces superfluid, like Giorgio said yesterday. So if m sub f is the mass of the displaced superfluid, we now have a natural way in this model of distinguishing between heavy particles, where this ratio is much greater than 1, neutral particles where it is 1, and light particles where it is less than 1. Let's say we keep the size of the particle fixed. All right? All right, numerical methods. Mark knows everything, so we'll trust everything he does. Okay? And it is important to prepare initial conditions properly. If you just naively, if I were running this the first time, I'd put in some random initial condition, it would be full of sound waves. But in Mark's group, for many decades, they have perfected this art of what they call the advective real Ginzburg-Landau equation. Okay, it's not even easy to pronounce this acronym. Okay, where you have some advection velocity, and then you apply it and you minimize things. The good thing is that with this, you can prepare very nice initial conditions which have hardly any sound waves to begin with. All right? Because note, if you did all the Madelung stuff, which I'm not going into because it's been done in several other talks, you will generate sound waves. So let me show you, depending on how much time I have left, 5 minutes. Okay. All right. So we'll go to the movies for 5 minutes. All right. I will show you vortex pair shedding when there's a constant external force acting on a single particle. I will tell you how two particles interact in this superfluid medium. Then I will make things more and more complicated. Many particles, interaction of a single particle with a vortex pair, and so on. So let's see how many of these we can get through, the details which you don't need to worry about. So here's a single particle. There's an external force which is accelerating the particle through the medium. And if you look at it over here, basically what this particle does, after it is sped up enough, it will shoot off some vortices. One of the vortices will get trapped on the particle, or you can say the particle is trapped in the vortex, depending on your point of view. And then as time goes on, because of this constant forcing, more and more sound waves are generated. And a movie shows things much better than I can say in words. So let me just show you this movie. Okay, so there's the particle, and then it goes beyond some critical velocity, shoot off vortex, capture vortex, so on and so forth. All right? So, yeah, the obstacle develops a circulation because of the vortex. Right? Am I correct in saying? Yeah, exactly. So it's doing nice things. You can do it for a light particle, you can do it for so on. I won't worry you with every detail. But if you look at the particle velocity, you see it increases with time. This is the x component. The force is in the x component, x direction. Goes and then at maximum and something happens. So this is where it has gone below the critical velocity and it is sent out a vortex-anti-vortex pair and so on. This is what it happens when you have neutral, heavy, and neutral it gets perturbed much more, as you can see, and light even more. And if you want to, and we have done all this, you can analyze these time series, and they can either be periodic or quasi-periodic or chaotic, depending on how much it has been perturbed by this motion. Okay? Now let's look at two particles. Initial separation of 7 healing lengths. Okay, and what are these plots telling you? This is the position of the particle, and this is the velocity. So somehow these two particles came and they coalesced. And these ones rebounded. Okay, this is with no short-range repulsion, and this is with repulsion. So somehow by repulsion, we are driving some sort of a transition between the energy components also you can look at, between an inelastic collision and an elastic collision. Actually, if you go through enough details, which I won't go through, you can compute attractive interaction, the superfluid mediated attractive interaction. You can compute it at the level of a Thomas Fermi approximation, and it's pretty good agreement. And so let me just show you a few movies. So the first movie will show you an inelastic collision. So here they come along, and that's it. All right? Okay. So that was inelastic. This is a very small repulsion. Okay, so now we do it. This is all, physics 101, except that the superfluid mediating hotel. But, yes. We just picked some number. We can change it. Yeah. Okay, I can go through the details with you. They're all written in the paper, but yeah, it's doable. Yeah, I'll show you. Give me a minute. I'll show you a plot also. Okay. Give me a minute. Perhaps Mark remembers right off. So you can look at energy components. So here, again, since we are doing physics 101, we define a coefficient of restitution. And if you plot it on the vertical axis, you can either plot it versus the strength of the interaction, or you can, the energy of the collision things, and you can plot it versus the strength of the interaction. And as far as we can tell, there's a continuous transition from a completely inelastic collision to an elastic collision. And the only reason I'm boring you with 101 physics is because there's an intervening superfluid which is giving an effective interaction between them. Right? Okay, you can do impact parameters. Again, elementary mechanics. If they're offset, you can get beautiful patterns which look like sunflowers and whatnot. Okay, so I won't trouble you. Now you can look at many particle dynamics. Wait, 1 minute, 2 minutes? 2 minutes, okay. Many particles. So we shoot the particles at each other like this, and their trajectories can get very complicated. So let me show it to you in this particular case. Okay, there. Initially, it looks like they're more or less going to rebound and so on, but eventually some symmetry gets broken, and once that happens, all right, that got broken. All right, I couldn't have predicted this with any amount of knowledge of elementary classical mechanics. Okay, and lots of sound is being generated. Could be whatever, or dynamically generated chaos. Hard to tell. Yes. Yeah, waves. So there's enough stuff happening there. You can look at many particle dynamics. You can do one particle, many things. So let me not give you every detail, but let me show you a single particle. No. Yes? Okay, I'll look it up afterwards and tell you. Yeah, it was heavy. I mean, otherwise, so let's look at this very nice initial condition. See, to prepare this initial condition requires all the magic of ARGLE, which has been perfected in Mark's group. So let me just show you, and this is my last slide. I won't put up my conclusions, but I'll be happy to take questions while you watch this movie. Thank you. Those small ones are vortices, the big ones are particles. And now they've went crazy. And there's the particle has captured one of the